Hey folks, in this short video, we're going to look at how to find the infinite sum of a geometric series. In other words, how do we add up an infinite number of numbers in a geometric sequence like this? Now, you first might be thinking, whoa, Mr. Horn, I don't see how we'd add up an infinite number of numbers. Wouldn't the sum always be infinity? And you're right, a lot of the time it is. So like if I have a common ratio of 2, meaning I multiply by 2 to get to the next term in my sequence, you can imagine we had 48 and then 96, and the number that you're adding gets larger and larger, and this one would have a sum of infinity for this sequence. But I want to represent here, what if r is 1/2? What if r, that common ratio, is a number less than 1? It's one of those fractions in between 0 and 1, so that we're adding a smaller value every time. You might still be saying, hey, wouldn't that still, because you're adding an infinite number of values, wouldn't that still get to infinity? And I think I've kind of used my PowerPoint animation skills as much as I can to give us a little bit of a geometric representation why this works. So imagine this box representing 1. Okay, so this represents 1. So if I were to start with 1/2, okay, that red area would represent the 1/2. And then I would add 1/4 to it. And then I would add 1/8 to it. And so I'm just moving down the line, adding the next term in the sequence, and it's getting smaller each time. You see, first it took up half the figure, then it took up a fourth, then it took up an eighth of the figure. And then we add a 16th and a 32nd and a 64th, and then that number just gets smaller and smaller and smaller and smaller and smaller, right? And obviously there's limits to how small I can make those values, but you see, because they're getting so infinitely small, the sum of all those areas for this particular equation or this particular situation is going to be 1. So this is just one example of how we can sum an infinite number of values and get a number that's not infinity. But our big caveat is that our R value has to be one of those values less than 1. That means the values in our series or in our sequence are getting smaller each time. Now we're going to actually derive the rule. How do you figure out the number that it would add to? And we're going to use this slide to kind of derive our rule, and then we'll do an example on the next problem, on the next slide. So suppose R equals 1/2, right? So assume we're multiplying by that 1/2 every time. I'm going to illustrate where our equation comes from, but I'm going to build on our understanding from the previous video. This is our video that describes the sum of a finite geometric sequence. In other words, if I wanted to add the first 20 terms, this is the equation that would do it. Now, the only thing here is let's take this relationship, which we've already established. We proved it in the last video. But now, what if this n value grows infinitely large? Like, for example, if I want to find the first sum of the first 20 terms, we'd put a 20 there. But how would this behave if that n grew larger and larger and larger? Well, let's come back to r, and let's evaluate r to the n, and see what happens is that n value increases. So we're going to do r to a larger and larger power and figure out what would happen to this as it grew very large. So r to the first power is just 1/2. 1/2 to the first is 1/2. But if I did 1/2 squared, that would be 0.25. If I did 1/2 to the third power, my r value to the third, it'd be 0.125. You see that by multiplying by that 1/2 over and over again, this value is getting smaller and smaller. Now what happens if n got infinitely large? What if it kept going? Now, what we're going to see is I know that we can't plug in infinity for n. I'm making this video for a pre-calc class, and we haven't quite talked about limits and things like that. But just picture what would happen. For now, bear with me. If we had r to an infinite power, 1/2, and when we kept raising it to that larger and larger power, this number would become functionally 0. This r to the n would basically become 0 as n got infinitely large. Well, what's 1 minus 0? That's going to be 1. And a sub 1 times 1 is a sub 1. So basically, to find that infinite sum of a geometric series, or of a geometric sequence, we take our first term and divide by 1 minus the common ratio. This is your formula. That's the thing we need to write down, okay? Label that sum of an infinite geometric series. Now, let's do an example on this slide. I've got our little relationship up here, and we're going to find the sum of, pardon my typo right there, but we're going to use this geometric sequence, and this is what we're going to do. So what we've got is we see that our number, we go from 50 to 30 to 18, and our r value in this situation is going to be 0.6. If you weren't sure that it was 0.6, that's the number we're multiplying by every time, just take 18 divided by 30, or take 30 and divide by 50. But r is going to be 0.6, and a sub 1, our first term, is going to be 50, okay? Now, all we got to do is we take our term to find the sum. We do our first term of 50 divided by 1 minus the common ratio, or in other words, 50 over 0.4. And where's it going? 50 divided by 0.4 is 125. So if I were to add the infinite number of terms, if I were to be able to hypothetically take this out to an infinite number of terms and add them all up, the sum would be 125.